Okay, good morning, everyone. All right, let's get started. I think it's time to start our lecture now. I'm gonna turn off my um, video. Okay, so all right, so on Tuesday we learned how we can use different version of the X matrix. For example, we can use different Z. We can use different scale for W for the additive or the dominant effects, and this will not affect uh, uh, our final hypothesis testing in terms of this genetic effects, right? And so I mentioned, so in the final, probably I can give you something like this. So I will give you a different design of Z variable and W variable, and I will ask you to show me, based on the definition, I will, I will ask you to show me why the expectation of Z and W equals to 0. And also, uh, uh, in different setting, probably you will have different variance for Z and W. So please do the calculation for the variance for Z and W. And also you need to calculate, you need to know how to calculate the covariance between Z and W. All right. So remember, this is a F2 population. So when we mention F2, so there's a hidden message, right? So this means like we have three genotypes, 1, 2, 3, and the proportion for the three genotypes should be 1/4, 1/2, and 1/4. Okay. Now today we're gonna learn something different. Uh, so we can use a different scale to model the linear regression for testing this genetic effects. So for example, if still we're talking about the F2 population, then we have three genotypes here. And if we can um, use the parameter beta 1, beta 2, and beta 3 to represent the average genomic, I'm sorry, the average genotypic effects for these three genotypes. So we can write a model like this. So this is the phenotypic value for a specific individual, let's say J's individual. And so we use three random variables here, xj1, xj2, and J3 to represent the genotypes. So for example, if the J's individual, for the J's individual, if the genotype is the first one, A1, then the first random variable X should be 1, indicating, okay, so this individual carries the genotype of A1. So on the same time, so the other two should be 0 and 0 because we knew this individual has the genotype like this, right? So for example, this is the first individual, let's say, and the second individual, and the third individual, and so on. So we have like 1,000 individual here. So for the first one, if we knew this one is the first individual, the genotype is A1, so we put 0, we put 1 for the X11, but 0 for X12 and X13. All right. Now for the second individual, if this individual has the second genotype, which is A1 and A2. So guess what? We're gonna put 0 for the first X, but 1 in the second X, and 0 in the third one. So let's look at the third individual. If the third individual takes the genotype of A2, so yeah, you're right. So we put 1 here, but 0 here and 0 here. So this is another way we can use to design the X matrix to indicate the 3 genotypes. So we call this kind of X. So because you see the X only takes value either 1 or 0. So we call this kind of variable as a dummy variable. Is that clear? Okay, so if you design your X matrix in this way, then we can use the matrix notation to represent this linear regression model, right? So the X should be what? So suppose we have 1,000 individual. So the Y should be a vector of 1,000 here, 1,000. And the X, can anyone tell me what is the dimension for X matrix here? What's the dimension?
Well, if it's the dimension for it shouldn't be it's the similar dimension to the one you showed on the right, a 3 by 3.
Now we have 1,000 individual here, so yes.
We have 1,000.
Yeah, we have 1,000. So
3,000 by 3,000 then.
I'm sorry, say that again.
Oh, then it would be 1,000 by 1,000.
1,000 by 3 actually.
1,000 by 3.
We have so for each individual we have 3 letters, right? So
yeah.
to show which genotype it has. So since we have 1,000, so this matrix should be 1,000 by 3. Does that make sense?
Yep.
Okay, great. So this is the dimension for the X and the beta. How about beta? So what's the dimension for beta? We have 3 beta here, right? So the beta should be 3 by 1, right? All right, so if you multiply X by beta, which is 1,000 by 3 and 3 by 1, so the results should be 1,000 by 1. So that matches the dimension for Y, right? Is that clear? And this is the random error, the measurement error. Okay. All right. And clear here. All right. Okay. Now this is the matrix notation. So the same, right? Although we use different scales, we use different way to design the X matrix. But still we can use, because this is a linear model, we still can use the least square or maximum likelihood estimation to estimate this beta. So beta is beta 1, beta 2, and beta 3. So this is the notation, matrix notation for the least square. And also we can calculate the random, the residual error, the variance for the residual error, right? And all right, now using this, we can calculate the variance of the beta estimation. Then what's the next step? So if we have the variance of the beta hat, and if we have the estimation for the beta, so what will be our next step?
Calculating the F statistic.
Yes, very good. So we're gonna create a test statistic by this ratio, right? Standard error of beta hat. This is one way, or we can take a square. So this is following a Watt distribution.
Chi-squared?
Yes, so Watt test, right? Chi-square. Very good. Very good. Okay, so is that clear on this slide? So this is another way we can design our X matrix to construct a linear regression model to describe the relationship between the phenotypes and the genotype and the genetic effects. And then once we have the estimation for this genetic effects and its variance, then we can construct a test statistic to help us test whether this genetic effect is equal to 0 or not. Is that clear?
The variance part is not.
So this part, I mean,
Beta hat.
oh, beta hat. Okay, let me.
And me.
All right.
I
So
don't know I don't know what T means here. I don't know what the letter T is for.
oh, okay, got it. Okay, so this is the matrix notation. Let's say matrix. So okay, so this is the matrix notation to represent the least square estimation for beta hat, and this is X matrix, right? So this X matrix, we put T here means the transpose of the X matrix. So in scalar, so when we say X square, which means like X multiplied by X, right? So this is the scalar square in the algebra. But when we talk about the matrix, we cannot just say this because these two cannot be multiplied like this. If we want to calculate the square of the X matrix, so we use this format. So the X transpose multiplied by X matrix. So that's equivalent to something like this. The same thing here. So we use X transpose multiplied by Y. So this is how we do this. And the minus 1 means like 1 over something, inverse. All right. Any other questions? Is that clear, right?
No, why are we calculating variance?
Oh, you mean here?
Yeah.
Oh, yeah, okay. So let's go back to our probably the lecture 5. So when we talk about the engineering, so we usually use the signal by noise ratio, right?
Yeah.
To test the signal. So in statistics, what do? We use the estimated B divided by the standard error of B, right? This B estimation represent the signal we try to pick up from the background noise. But this standard error represent the noise, right? And what is the standard error for this? So this is associated with this. So if we want to calculate the standard error for the B estimation, we first need to calculate the variance of the B estimation, and the square root of this guy is the thing in the denominator. So this is how we construct a statistic for the testing. Is that clear?
Now, why are we doing this, and why does this have to relate to an F statistic and a chi-squared test?
I'm sorry?
Why are we doing this, and why does this relate to an F statistic and a chi-squared test?
Oh, okay. So this is related to, let me show you. Okay. So probably there's a disconnection between lecture 5 and lecture 6 for you, I think. So let's try to reestablish this connection here. All right. Okay. So what is the what test we try to do? First, so we want to do this, right? The B estimation for the signal, and the B square divided by the variance of the B square, the variance of the B hat. This is a chi-square distribution, right? Oops. Degree of freedom equals to 1. Suppose this is only a single B1 and 1 minus alpha, right? So to construct this chi-square statistic, we have to calculate this variance, right?
Yes.
Do you still remember?
Because the wald test is equivalent to a chi-squared.
Yes. So let me go back to here. Probably, yeah, it's clear here. So
well, it's equivalent to an F test. It's equivalent to an F test, but it's not. But it relates to a chi-squared test somehow.
Okay. So do you still remember this slide? Let me show you. So this is what we discussed before, right? So, okay, so here we have, let's say we have a single parameter to test, right? This is the additive effect. This is how we calculate the B hat, and this is how we calculate the variance. So this is exactly what I mentioned there, right? And so if we form a ratio, this is a F test. And because the F test is the degree of freedom for the first degree of the freedom equals to 1, so this is exactly equal to the chi-square test with degree of freedom equals to n-2. And is that correct? So did I have I refreshed your memory?
Yes.
So here, so this is what we learned before. So if we want to test this bit, the B1 hat, the additive effect, we want to construct the F statistic using this ratio. So the ratio, the upper, the numerator of the ratio is the B estimation square, right? And if you look at the denominator, that's the variance of the B estimation. And because we're only test one single B, so this F distribution is equivalent to the chi-square distribution with the same degree of freedom, n-2. All right, clear?
Yep.
Oh, okay, perfect. All right. So if you compare these slides to here, they're the same. Not here. Oops, where is it? Oh, I lost my track. Where is it? Yes, it's here. Right? So they're the same. So we estimate beta and we estimate the variance beta. Then we can construct the beta hat divided by the beta. This is the F test, right? If the beta only consists of one variable to estimate, so this is the same with the chi-square. Okay. All right, let's move on. Okay, so as I mentioned, so if you use different design matrix, it will not affect your final hypothesis testing. So this is the way we show. So when we use the beta 1, beta 2, and the beta 3, the dummy variable to describe the linear model. So once we have the estimation for beta 1, beta 2, and beta 3, so we can use this estimated parameter to estimate the original parameter we would like to estimate, right? So here the additive effect is A, and the dominant effect is D. So we can easily calculate the estimated value for additive effect or for the dominant effect using the estimated beta 1, beta 2, or beta 3, and beta 3. Okay, so this is the matrix notation. So how we can connect the originally defined the genetic effects with the newly defined genetic effects, right? So this is the linear relationship between these two, and this is the A matrix here. And so we can use this matrix notation to reflect the relationship between the originally defined genetic effects and the new genetic effects with this linear combination. So now if you want to test any genetic effects here, the additive or dominant, so you use this equation, the formula. So this will give you the same test results. So any questions here? Any questions?
Notation clarification. So the A is focusing on the first matrix, That matrix, that's the representative for the first matrix, A bold, A in bold.
That's right. That's the
But but is this focusing on, is that matrix representing the genotypic effects, or is it just
uh,
representing, you know,
okay. So this is clear, right? This is how we define the genetic effects, right? So in the past, we learned. So suppose this is the initial model we use.
yep, Y mu plus Z.
Right? This is the initial model we have been using in the past, right?
Mm-hmm.
Okay. Now, so because in the previous slides here, we try to set up the linear model in a different way. So as I mentioned, so we can, so using different ways. So to design the linear model, we will not change the test results, right? So in this case, we use 1 to beta 1 plus x2 beta 2 plus x3 beta 3 plus. So we use two different linear models to describe the relationship between Y, which is the phenotype, and the genotypes, which is using different way to code, right? Okay, now, so since these two way will give you the identical test results, let's see what's the relationship between this estimated effect here with this version of the genetic effects, right? In this model, we just use beta 1 to represent the average genotypic value for the first genotype. Beta 2 is the average genotypic value for the second genotype, and so on, right? So, okay, so if we use different model, so what's the relationship between these parameters? So this is the relationship. When you use the second model to estimate this genetic effects, they are actually associated with the originally defined genetic effects. So what's the relationship? This is the relationship. We use the A matrix as a regression coefficient to link the original B with the beta here. Is that clear?
Yes, that makes more sense.
Yeah, all right. So because if you use the first model, you should calculate the variance of the beta hat to construct your test statistic, right? But if you use the second model, so this is what you can construct, right? For the beta hat variance. But what's the relationship between those two? So this is the relationship, right? I just want to show you. So if you use different way to design your X matrix, so you may end up a little bit different estimation for your parameter, but different model, they are related to each other. So this is the relationship between the model 1 and the model 2. Okay. I hope it is clear. So any questions, problems? Good. Okay. Very good. Okay. So so this is one way. Last time on Tuesday we talked about, so we can use this way to design your Z variable and the W variable, right? Okay. Now if you use this setting, and this is the model 1, and you use model 2, which is the beta 1, beta 2, and the beta 3. So if you use these two models, then the relationship between this genetic effects parameter with this genetic effects parameter is associated with this A matrix. which means if you use this design for your Z variable and the W variable, the A matrix will become like this. Any questions?
How can we get what element needs to be added to matrix A? Like how to calculate these numbers? How can we come up with this?
Oh, you mean how can we? Okay, sure. Let me show you. Oops. Okay. You mean so? Okay, good question. So, for example,
Yeah, for
here,
this one, I think it's easy because I can use these relationships.
there's
Or
B2 is 0, right? So that's why
Yeah.
0 is here.
yeah.
Yeah. Okay. The same thing. I think so. So basically, you need to find the relationship. So once you have the beta 1, beta 2, and the beta 3 estimation, right?
Mhm.
So you need to find the linear combination of these three to
Mhm.
express each of these parameters. So in this case, if you design a Z matrix and a W matrix like this, so I'm pretty sure, so you can express your mu using 1/4 beta 1 plus 1/2 beta 2 plus 1/4 beta 3. And so if you want to estimate the additive effect, this should be square root 2/4 beta 1 plus 0 plus beta 2 minus square root 2/4 beta 3. So yeah, so this involves how you can find the linear combination between these two sets of parameters.
Yeah.
Okay, that's the A matrix. Oops. Yeah. And so on. So if you do this thing, so you're gonna use these three numbers, right? So 1 minus 1/4 minus 1/4 beta 1.
Yeah, got it.
Yeah, 1/2 beta 2, and then 1 minus 2 beta 3. Yeah, something like this. Okay, any other questions? Okay. All right. So far we have learned how we can. So each one can use different way to design your linear model and the random variables. Like for example, if you would like to use the original genetic effects, which is the midpoint mu, and additive effect A, and the dominant effect D. So you can choose different way to code your Z variable and the W variable. However, if you want to use the dummy variable, so you that still work, right? So you just use 1, 0, 1, 0, and you use beta 1, beta 2, and beta 3. So whatever you need, the linear model you use, whichever linear model you're going to use, you follow the same strategy. You just use the least square estimation to estimate the beta hat, or the b hat or the beta hat, and then you use still use the same strategy to calculate the variance of the residual error. Then you can calculate the variance of the estimation for either the B or the beta, right? And then you can use the ratio to construct a test statistic. You're almost done. So when you get that, so we're gonna perform a test. So now let's look at the test, right? We're gonna talk about test. So I hope like the logic I try to use for teaching is clear. Is there any question about this logic flow? So first, we got the data, and we used the linear regression model to describe the relationship between the phenotype and the genotype, right? We can use different way to do that, but no matter what way you use, we can always use the least square to estimate the genetic effects, and we can also estimate the variance for that, and then we construct a test statistic. We use that to do a test. Now we're going to look into the test. Any questions? All right. So when we constructed, so if once we successfully constructed a test statistic, so we're gonna use this statistic for a test. So I hope you still remember. So the diagram I showed you before. So the test statistic is actually your data, the information you summarize from your data, right? So the data is yourself. You fit yourself into one of the two dresses. So we have two beautiful dresses here. One is the H0, the non-hypothesis, the first dress. And we're gonna put this dress on ourselves for a test. We do not have time to fit to try the other dress. So we're gonna put the first dress on us to see if ourselves, our data fit the dress well. If not, we're gonna reject the non-hypothesis, the first dress. We're gonna accept the second dress. I hope you still remember this, right? This is the procedure we always use for hypothesis testing. So in this procedure, so there are two possible errors we could commit. Type 1 error and the type 2 error. So the type 1 error, actually, there's another name for type 1 error, is the false positive. Type 2 is the false negative. All right. Yeah, I love this diagram. This cartoon. So it's interesting. All right. Okay, so now forget about the cartoon. So let's look at our let's go back to our business. So here we try to do what? We try to test if this locus is associated with the phenotype of interest, right? So we want to test if, for example, if there's an additive effect at this locus, which account for the variability in the phenotype, right? Okay, now what is the type 1 error here? So suppose the type 1 error here is suppose H0 is true, which means the dominant, so I should put A here. So, okay, let's use the dominant. Okay, so suppose the dominant effect is genetic effect is 0, which means this gene is not associated with the phenotype, right? Okay, so there's no association between the genotype and the phenotype, but your test claimed an association between this locus and the phenotype. What does that mean? That means like if H0 is true, there's no genetic effects, but your test says, okay, there is a genetic effect. That's the type 1 error. So type 2 error is another situation, right? So if H0 is not true, which means your alternative hypothesis is true, and there is a strong association between this locus and the phenotype. However, based on your data, based on your test statistic, you claim D equals to 0. So when there is a association between the locus and the phenotype, but your test does not claim an association between them. So that's another type of error. Is that clear? Good. Okay, so I hope you have this table. So I took this table from the textbook. I think, yeah, it is very helpful for us to understand the relationship between the type 1 error and the type 2 error. So suppose in this table, this, so the row represented the real situation. Either the non-hypothesis is true or the alternative hypothesis is true. And so the columns of the table represent the test results. So, okay, based on the data, what will be the claim from your test? Either you accept the non-hypothesis or you reject the non-hypothesis and take the alternative hypothesis. Okay, let me erase this notes here. Okay, so let's see. So if we have two true situation, and for each test we have two possible outcomes, right? Test results. So this will give us 4 possible combination, right? Either the non-hypothesis is really true and our test gives you the right conclusion. So this is one situation, and this is the correct test results, right? There's another situation when the non-hypothesis is not true, but your test is correct as well, and your test will reject the non-hypothesis and take the alternative hypothesis. So in this table, the diagonal element is the correct test results. However, if you look at the off diagonal here, let me see. Okay, so this situation and this situation, this represented the two incorrect tests. So if the non-hypothesis is true, but your test rejected the non-hypothesis and take the alternative hypothesis, that gives you the type 1 error. So alpha represented the type 1 error. And the type 1 error is defined as the probability that given the non-hypothesis is true, but you rejected the non-hypothesis. So this is type 1 error. So type 1 error is actually a probability. Type 1 error alpha is actually defined as a probability of what? Of the probability of this. So given the non-hypothesis is true, but you rejected it. So then if you understand this, so the type 2 error is easy to understand, right? The beta is the type 2 error, which is opposite. So given the non-hypothesis is not true, but you accepted the non-hypothesis. This is another way that you that your data could give you the wrong conclusion. And there's another very important concept in statistics, which is called the power. The statistical power for a test is defined as the probability that, so the probability of what? Of this. So this is the power, the probability that given the non-hypothesis is not true and you successfully rejected the non-hypothesis, what's the chance for that? So this is the power. So power is equal to 1 minus beta, because this, the whole thing add up to 1. So if you want to calculate W, so it's 1 minus beta here. Is it clear?
Could you clarify the statistical power?
Okay, sure. Give me a second. All right, statistical power. So, okay, let me give you an example. I think, yeah, probably example is better for us to understand this. So suppose we are, so in our lab, some students are working on the prostate cancer, right? So, so let's say, so there's many thousands of genes. So you want to, so you have a sample. So for example, you have like 100 normal sample, and you have another 100 tumor sample. Okay, so you want to, so for each sample you get maybe 20,000 gene expressions, right? Okay, now based on this data, you want to test each gene, whether this gene is associated with the tumor Or in another way, you want to see if you want to test each of this gene to see if a gene is differentially expressed between the normal sample and the tumor sample, right?
Yes.
Okay, so this is what we want to test. So suppose we want to test the gene 1. Okay, you have 100 values for gene 1 in normal. Is that right? You have another 100 expression values for gene 1 in tumor samples, right?
Mm-hmm.
Okay, so if you want to do this test, so you have to have a non-hypothesis. What is your non-hypothesis here?
Since we're looking for something differentiating, our null hypothesis would be that we're going to see
same,
that
right?
values are the same.
Yeah,
Yeah, similar.
the there's no difference. That's the non-hypothesis. Very good. Okay, all right. So this is the non-hypothesis. Okay. So this is something we want to test, right? Okay. Now, what is the alternative hypothesis?
That there will be different values for these two sets.
Yes, very good. So n is not equal to tumor, right? Okay. Now, so so given this, because we do not know reality, only the God knows the truth, right? So suppose okay. So for this test, there are two situations. Suppose there is no difference between the tumor and the normal tissue regarding this gene. So this will be the grand truth, right? There's no differential.
Mm-hmm.
Okay.
Yep.
Now, but when you test this, so suppose this is the truth, but you probably can get different data, and different data has chance to produce two kind of conclusions, right? Either the data gives you the right the right conclusion. Yeah, the data also shows okay, there's no difference. Then this is the situation, right? Given the truth is non-hypothesis and you accept it, so that's the probability, right?
Mm-hmm.
There's another probability that even the truth is that there's no difference between these two genes, but you rejected this non-hypothesis. That's another probability, right?
Yeah. That's
okay. So that's the type 1 error. So is that clear? So given this gene,
I understand type 1 and type 2. I get those completely.
Oh, okay, great. So
it was statistical power I was asking about.
Yes. So because I try to like build up this. So if you understand this part, then this is the same. So suppose we're talking about another gene. So that gene got news that gene is differentially expressed between tumor and the normal. So that's the truth. But for this true gene, so you still can get two possible conclusions based on test, right? Either, yeah, you get the right conclusion, given this gene is differentially expressed. Your data also tells you this gene is differentially expressed. So you reject the non-hypothesis, which says this gene is not differentially expressed, right?
Mm.
Okay, that's the power. So power is the probability that how likely you're gonna reject the non-hypothesis if the non-hypothesis is not true. That's the power. Or in another way, it says if a gene is differentially expressed, so what's the power or what's the chance you're gonna successfully detect the difference between the normal and the tumor?
Got it.
Okay, that's the power. So this is another term we are very interested in statistical testing because we want to design a test which is powerful to help us identify the differentially expressed genes between tumor and the normal. We want to increase power, but we want to reduce the both type 1 and type 2 errors, right?
Mm-hmm.
Mm-hmm. Very good question. So any other questions associated with this slide? Good. Okay, now, so this is another example. So I think this. So let's talk about this example. So hopefully this will help us to better understand the concepts here. Suppose this is a experiment for testing whether a drug, for example, like the so whether a drug is effective in decrease the blood sugar level. so the data the data is like this. So we recruit a group of patient, and this is the patient ID, and for each patient we measure the blood sugar level before the drug and the post drug. Okay, post use of the drug, and we have to pair the data, right? And for each patient, we can calculate the difference. So for example, for this one, we did see a reduction in the blood sugar, right? Blood glucose. And then we say, okay, so this is a positive reduction. So we use 2 here. So it has been reduced by 2 unit. Okay. All right, so for the second patient, we see 1 unit reduction, and the third one, but for the fourth one, it's interesting. So we say increase. So then we put a minus here. So this is the data we have. So we got so many data here. We want to see if this data can help us test whether this drug is effective or not. All right. So based on this, we can construct a non-hypothesis versus a alternative hypothesis. So what is the non-hypothesis here? Can anyone tell me?
The drug is not effective.
Say that again, I'm sorry.
The drug is not effective, like there's no change.
Yes, very good. So we can say the non-hypothesis is equivalent to D equals to 0. So which means that the reduction value is equal to 0, right? So we want to test if this thing is actually equal to 0. Is that right? So then we can form a non-distribution here. So the first address we want to use is the blue address, right? It is centered at 0, but with a little bit like a variability. Why is that? Because if there's no effectiveness of this drug, you still can see some turbulence or the variability in these numbers. Is that correct? Is that clear?
Yes.
Okay, so suppose this is the non-distribution we want to test, and we have a alternative distribution like here. So we have 2 addresses here. So we want to test the first address, the blue address, to see if our data fit this address. If our data fit this address, which means like it gives you a big p-value, that which is equivalent to, okay, if the non-hypothesis is true, if the drug is not effective, it is very likely to see the data like this, right? Okay, however, if your data does not fit the blue dress, then you're gonna reject the non-hypothesis. You say, okay, the p-value is too small, which means given the non-hypothesis is true, the chance of observing this kind of data is very low. Then I'm gonna reject the non-hypothesis and take the alternative hypothesis. We're gonna take the orange dress. Okay, so let me ask you a question. So if this is your data, and if you calculate your data, that if you calculate the average of your data equals to 2.3, and the standard deviation of this is about like 1, So something like this. So you use this data to calculate a statistic. So this is the statistic you got, right? 2.3, something like here. Do you believe your data is supporting your null hypothesis? What do you think?
Probably not.
Not, yes. I agree with you. I cannot agree with you more than that. So, because if you look at these two distributions, so this normal distribution gives you the density, the probability density, right? So if you got a statistic at this position, 2.3, so the density for the non-distribution is only this high. Something here, right? But if you look at the density of the alternative distribution gives you this high, which means the chance that if you got the data like this, the statistic is equal to 2.3, the chance that this data came from the second distribution, the orange distribution is this large, but the chance that the data came from the blue distribution is only here. So of course, we believe this data is not supporting your null hypothesis. Is that correct? Okay,
Yep.
in that case, so this area, so we're gonna talk about this later. So this area, so the area under the curve, the blue curve, beyond the statistic you got from your data is called the p-value. So in this case, do you think p-value is large or small?
Very small.
Very small. Yes, very good. So the p-value is something similar to the statement like, okay, given the null hypothesis is true, or given the drug is not effective, then the chance of seeing this data, of which the average equals to 2.3, is extremely low. Do you believe so? Okay, so in this case, of course, we're gonna reject the null hypothesis and take the alternative hypothesis, right? So which means what? What is your conclusion if you see the data like this?
The drug is effective.
Yes, very good. Is that clear? Anyone has any questions here? I hope, yeah, this example can give you a clear clue about the statistical testing. All right, let me give you another example. So suppose we do another experiment using the same patient, but we got this data, but when you calculate the average for this data, the statistic, so this is not the statistic. When we calculate the average, is only like 0.8, and still like the standard deviations